Okay, continuing our talk about probability and moving into what's called compound event probability now. So, central questions for this one: what is compound event, or what is a compound event, and how do you find a probability of one? And then how can you determine the total number of outcomes in a compound event, and then what is the difference between an independent and a dependent compound event? So starting off, we have blank probability when the probability is only based on a single event. And this is the type that we've been working with so far this week and in the other set of notes, and that would be simple probability. And so when there's only one event, such as in the example here, the probability of getting heads when flipping a coin once. So if you only flip the coin once, and we're talking about just finding the probability of that event happening, that's one single event, and so that's simple probability. The other type, as stated in the note, or in the title of the notes, is compound probability. So with compound probability, when the probability is based on two or more events. So if we have multiple events taking place that are going to affect the outcomes, then it's called compound probability. So a couple different ways that compound probability can be shown to. So this could be performing the same act multiple times, though. Okay, so if you're just doing the same act, so for example, the probability of rolling a die die twice and getting threes both times. So if I roll the dice once and it comes up as a certain number, say it comes up as a 3, and then if I take the same dice and roll it again, it comes up as a 3 again. So it's doing the same act multiple times for that. Or it could be two or possibly more separate acts. So, for example, the probability of drawing a 4 from a deck of cards and then rolling a 5 with a die. So, two different events or two different acts that make up the overall probability here. Okay. But in any case, either one of those would be an example of compound probability. Okay, so next we're going to draw a tree diagram, to show all of the possible outcomes from flipping a coin 3 times. Okay, so if I flip a coin once, flip it, and it comes down and lands, it has two possibilities. It can land on heads, or it can land on tails. And so that's my first option after the first flip. I have two outcomes. But then from there, and this is why it's going to be called a tree diagram, because we're going to branch those into the next option. When I make my second flip, depending on what I got on my first one, I could follow any one of these branches. So I could flip a heads, and then on the second flip, end up with another heads. Or I could have flipped the heads on the first one, and then ended up with a tails, in which case we would have heads so far, and heads tails after our second flip. And then for the tails, I could get tails in the first one, but then flip heads on the second. And then if I flipped tails on the first flip, I could also flip tails on the second. So notice now after flipping once, I had two options, or two outcomes. Now after flipping twice, there's actually 4 outcomes that I could have ended up with. And then each one of these, when I make my third flip, is going to have 2 options. So, after flipping heads twice, I could, on my third flip, also end up with heads. So this option would be if I got heads all 3 times. I could flip heads twice, and then on the third flip, get a tails. if I had heads on the first flip, tails on the second flip, and then I could end up with heads on the third flip. Heads, tails, tails is another option. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads, or tails, tails, tails. Okay, and that would show all of my possible outcomes then from flipping a coin 3 times. So how many possible outcomes were there for flipping the coin 3 times? Well, if we count these up, 1, 2, 3, 4, 5, 6, 7, 8 total. And then what is the probability then of flipping 2 tails and 1 heads? Well, the ones that have 2 tails and 1 heads, let's see, there's only 1 tail, but here's 2 tails and a heads, 2 heads and a tails, here's 2 tails and a heads, and here is 2 tails and a heads. So the probability of doing that would be 3 out of 8, or if you wanted to convert that over, 0.375. But there's our probability. Okay, so this is a compound event because we're taking the same act and doing it multiple times to figure out the overall probability of things happening. Okay, the fundamental counting principle as it's known. So what we were noticing there is that each time there were 2 options for flipping the coin. You could either end up with heads or tails. But what that causes on the first flip there's 2 outcomes. On the second flip there is 4 outcomes. So 2 here, 4 here, and then we ended up with 8 total outcomes on the third flip. Now, how we can get from 2 to 4 to 8? Well, if you think about it, multiplication, if I multiply this by 2, that gives me 4. And if I multiply that by 2, it gives me 8. So to determine the total number of outcomes in a compound event, we can multiply the number of possible outcomes from each event. So up here, the first flip had 2 possible outcomes. Multiply that by the number of possible outcomes from the second flip, which independently, so thinking about it not, so I know there were 4 possible outcomes here total for the second flip, but flipping the coin itself the second time, there's 2 possibilities that can come up when you flip the coin there. And then the same thing for the third event. Flipping the coin once again, that has 2 possible outcomes. So in all together, 2 times 2 times 2 gives us 8, and that's how many total possible outcomes we have. Okay. So, it says to determine the number of possible outcomes or combinations of the following events. And so here we have some of the compound events where there are separate acts. In this first one, we have beverages. So you have size options of small, medium, and large. And then you have flavor options, root beer, cola, diet cola, iced tea, lemonade, water, and coffee. And so to figure out how many total combinations you can make out of those, all of those things, well, for the sizes, we have 3 options. And if I multiply that by the number of flavor options I have, 1, 2, 3, 4, 5, 6, 7, I come up with 21 possible outcomes. Okay. Now, if we were to do our tree branching diagram idea, we would have to do a small, a medium, and then a large. And then because there are 1, 2, 3, 4, 5, 6, 7 options, each one of these would have 7 branches. Okay? And that's why they each lead to a flavor. And so if there were 7 possible options here, 7 possible options here, and 7 possible options here, that's again why we end up with 21 possible outcomes there. Over here for number 2, we've got a clown that has options of the suit that they're going to dress in, so either dots, stripes, or checkerboards. So there's 3 options there, or 3 possible outcomes. The wig, either one color or multicolored, so that's 2 possible options there. And balloon animals, juggling, unicycle, or magic for the talent, and that would be 4 there. So if I multiply all of those together, get 3 times 2 times 4, but that would be 6 times 4, and so that's 24. Possible combinations. Okay, independent and dependent compound events. So an independent compound event, the result of one event do not affect the result of other outcomes of other events. Okay, so whatever happens in one of the events does not change the outcomes or change the probability in the other events. So going back to our coin flipping idea, that was an example of that. Every time you flip the coin, you had 50-50 chance of it being heads or tails. So there were 2 outcomes every time. So another example here, the probability of rolling 2 odd numbers on a die. Both times the numbers 1 through 6 are available to roll. So if I roll the die once, I have numbers 1 through 6 available to me. If I pick it up again and roll it again, numbers 1 through 6 are available again. So they're independent compound events because each time the number of outcomes is going to be the same no matter what you did on the first event or the first act. Dependent compound events, the results of one event do affect the results or possible outcomes of another event. So here's an example. The probability of grabbing 2 red marbles from a bag that contains red and blue marbles without replacing the first marble that is drawn. So if I have again a bag of marbles, I reach in and I grab one out, there's red and blue marbles in there. If I grab a red marble on the first one and I keep it out of the bag, I've now changed the overall number of marbles that are in the bag. So by not replacing it and putting back in, I've changed the probability or the possible outcomes, the number of possible outcomes, on the second one, because there's 1 less marble in the bag. So it explains that here. After drawing the first marble, the number of favorable outcomes changes and therefore changes the probability of drawing another red marble. Thus why this is a dependent compound event. So the other set of events is dependent on what happens in the first one. So in these examples, we're going to state whether the following compound events are independent or dependent. On a shelf, there are 60 novels and 20 poetry books. What is the probability that a person chooses, or person A chooses a novel and then walks away with it, and then person B walks up shortly after and picks another novel? Well, since person A took their novel, walked away, and they didn't replace it, that means it's going to affect the probability of the second person choosing, and so this is going to be dependent. Number 2, Diamond is playing a game. In the game, she has to spin a spinner that is divided into equal sections of orange, red, purple, and pink. What is the probability that on her first spin, she will land on pink and then red on her second spin? Well, since the spinner doesn't change on the second spin, it's not like the red option gets taken away, the probability is going to be the same no matter what she does on the first one. So this is an independent event. Number 3, what is the probability of rolling a 4 on a number cube and pulling a red marble out of a bag that contains 3 red, 2 black, and 5 yellow marbles? Well, since you're rolling a number on what they call a number cube, that's like a die or a dice, and then pulling a red marble out of a bag, the number of marbles in the bag doesn't matter what you do with the dice, so it does not affect the outcome of the second event, and therefore this is again independent. Number 4, numbers 1 through 20 are placed in a bag without replacing the first number. What is the probability that the first number drawn will be odd and the second will be even? Again, the key here is without replacing. So the fact that you're not putting the number back in after you draw it the first time, that is going to alter or change the probability of the second event, and so this is again dependent. Okay, so finding the probability, or the overall probability of a compound event then. So we're first going to find the ratio for the probability of the first event. Find the ratio, again, for the probability of the second event. And then simply need to multiply the two ratios or probabilities together. Now, if you have more than just two events happening in the compound event, if there were 3 or 4 or 5 or 6 or however many it is, we just continue to multiply those together. Okay, so first an example where it's a dependent event example. So we put 2 red counters, that's like just little tokens or something, and 2 white counters in a bag. What is the probability, P, of choosing a red counter, not replacing it, and then choosing a white counter? So first, find the probability of the first event, P for red on the first draw. Well, there are 2 red and 2 white counters, so there are 4 possible counters. And the first event, we are choosing a red. And so what is the possibility of choosing a red on the first draw? Well, there were 2 in there, so that's 2 out of 4. Or that would be 50%, 1/2. Step 2, find the probability of the second event, which is probability of drawing a white on the second draw. But remember, we're not replacing. So what's left in the bag? Well, at this point there would be 3 counters left total, and 2 of those would be white, because we had already drawn out a red. So it says, remember here that we have 2 white counters remaining out of the 3 total counters that are left. So now we multiply the 2 probabilities together. If I multiply 2 fractions, remember I just multiply top times top, bottom times bottom. Don't have to make those common denominators. So 1 times 2 makes 2, over 2 times 3 makes 6. I get 2 out of 6, or if I reduce that, divide both by 2, that would be 1/3. So my overall probability of first drawing a red and then drawing a white without replacing is 1/3. So an independent event example. If we put 2 red counters and 2 white counters, so same scenario to start with, what is the probability of choosing a red counter followed by a white counter? With replacement, putting the red counter back in. So this time now replacing it, so that the number of total counters each time you draw stays the same inside. So find the probability of the first event. Well, once again, it's the same. 2 out of the 4 are red, which is 1/2. Then find the probability of the second event. Remember, we still have 4 total counters. 2 are red and 2 are white. So in order to draw a white one this time, it's going to be 2 out of my 4, or 1/2 again. And now multiplying straight across. This time, the probability of drawing a red and then a white with replacing is 1/4. Okay, in our examples, find the probability of each event. So Ricky takes 2 coins at random from 3 quarters, 5 dimes, and 2 nickels in his pocket. What is the probability of pulling out a nickel and then a quarter without replacement? So without replacement, well, in the first one, for pulling out a nickel, there are 2 nickels. So it's a 2 out of 3, and 5 makes 8, 9, 10 total. Which, if I were to reduce that, reduces down to 1/5. So he's got a 1/5 chance of drawing a nickel, and then a quarter, but without replacing. So now instead of there being 10 coins left, there's only 9. And he's drawing a quarter. There's still 3 quarters in there. So 3 out of 9 chance, which reduces down to 1/3. And now if I multiply those together, 1/5 times 1/3, we get 1/15. So he's got a 1/15 probability of first pulling out a nickel and then a quarter without replacing. Number 2 is what is the probability of pulling out a quarter and then a dime with replacement. So there were 3 quarters out of the possible 10 coins to choose from. That one's not going to reduce. Now we're going to replace the quarter if we drew it. And so there's still going to be 10 in the second event. And a dime this time, well, there were 5 dimes. And so that's 5 out of 10, or that reduces down to 1/2. And so 3/10 on the first event times 1/2 on the second event. And that gives us 3 out of 20 as our overall probability of choosing a quarter, replacing it back in the pocket, and then choosing a dime. Okay, in the conclusions. So what is the difference between finding the probability of a simple event versus a compound event? So, simple event is only based on one event, and compound events are based on multiple events. How many possible outcomes are there flipping a coin 5 times? And then how many of those outcomes are at least one heads flipped, or contain at least one heads flip? So if I flip the coin once, there's 2 possible outcomes. If I flip it again, on the second flip, there's another 2 possible outcomes, so I'd be up to a total of 4 now, right? Because I'm multiplying these together. There's 3, 4, and 5. So each flip, there are 2 possible outcomes. So if I multiply these together, good morning, Brindley. I'm in the middle of making a video here, though, this time, so I'm not talking to people. I'll be talking to people a little bit later, and then you can come back and say hi, okay?
Okay, but maybe tomorrow you can.
Yes. Why don't you go in and see Mom?
Sorry. Sorry, Dad.
That's all right. All right, so multiplying these together, I multiplied 2 times 2 to make 4 there, 2 times 2 to make 4 there, and then we have this other 2 left over that it still needs to multiply. So that would be 4 times 4, which is 16, times 2, and so we ended up with the possible 32 outcomes. So 32 different outcomes from flipping a coin 5 times. How many of those outcomes would contain at least one heads? Well, if we think about back to our example that we made on the front, and we look at these, all 7 of these have at least one heads. The only one that's not going to have a heads is the one where I'm only flipping tails. And that's going to hold true throughout this as well. And so only one of these options would not contain a heads, and so that means that 31 out of the 32 possible outcomes will contain a heads. Okay, number 3. Each student is given a different number in a class of 20 students, and then the teacher draws a ticket with the numbers on them one at a time. If the teacher does not place the number back into the bag after drawing a number, A, what is the probability of a student having their number drawn on the first draw? Well, there are 20 students with each an equal chance, and so that would be 1 out of 20. B is what is the probability of a student having their number drawn if 4 other numbers have already been drawn. Well, if 4 other numbers have already been drawn, that means we could take away 20, 19, 18, 17, and so that means numbers 1 through 16 would still be in there. So now your chance is 1 out of 16. C, is this an example of an independent or dependent event? Well, after the number is drawn each time, it's not getting replaced, and because of that, it's changing the outcomes of the next student's probability of being drawn. And so this is a dependent event then. Okay, so I wrote dependent because the number of possible outcomes is changing after each number is drawn. Okay, and then finally in summary, when probability is based on more than one event, it is called a compound event. To find the total number of combinations of possible outcomes in a compound event, we multiply the number of possible outcomes of each event together. If the possible outcomes are the same for each event after they are performed, it is known as an independent compound event. And when the possible outcomes change for an event after the other is performed, it is called a dependent compound event. To find the overall probability of a compound event, we multiply the probability of each event together. Okay, so the worksheets that we have on compound events will be posted up as well, so make sure you're going and practicing with those. Quiz should be up either later today or tomorrow, and make sure that you're ready to take that. Keep answering the daily questions as well, as that is part of your task.